Welcome to The Explainer. Today, we're uncovering the secret life of liquids. Specifically, we're talking about viscosity and surface tension. You know, whether you're pouring your morning coffee, washing your hands, or literally just sitting there as blood pumps through your veins right now, there are these invisible forces at work dictating exactly how those liquids behave. So let's unpack the physics behind them, focusing specifically on how we measure these forces in two classic 11th grade lab practicals. Let's get into it. Okay, let's dive into this. Have you ever noticed how different liquids kind of have completely different personalities? Think about it. You tip a glass of water and it just splashes out instantly. But if you tip a jar of honey, man, it takes its sweet time, just slowly oozing down the side. So why is that? Well, it all comes down to the internal molecular makeup of the liquid itself. It's an everyday observation, sure, but it sets up this massive concept in fluid dynamics, internal fluid friction.
And that internal friction, that's what we call viscosity. Basically, viscosity is the measure of a fluid's resistance to flow and deformation. You can kind of picture it as the liquid literally fighting against itself. So a fluid with a large viscosity, like our honey or, say, castor oil and glycerin, well, it resists motion because its molecular structure creates a ton of internal friction as the layers of liquid try to slide past one another. On the flip side, a fluid with low viscosity, like water, flows super easily because there's very little friction when it's in motion. And this brilliantly illustrates the physics of what happens when an object tries to move through that sticky internal friction. This right here is Stokes' law in action, and it's not just some boring math equation, it is an epic tug-of-war happening on a microscopic level. When a spherical object, let's say a small steel ball, falls through a viscous medium, it doesn't just drop freely. I mean, gravity is pulling it straight down, for sure, but fighting back against gravity are two upward forces. You've got the natural buoyancy of the liquid, and you've got the viscous drag force exerted by the surrounding fluid, which is basically pushing back up against the sphere's motion. It's an absolute battle, downward force versus upward forces. Gravity is trying to accelerate the ball, making it fall faster and faster. But here's the catch. As the velocity increases, that viscous drag force pushing up, it also increases. And eventually, those forces perfectly balance out. Gravity perfectly equals buoyancy plus viscous drag. Now, when this tie happens, the sphere stops accelerating entirely. It keeps falling, yeah, but at a constant maximum speed. And in physics, we call that sweet spot the terminal velocity. So, how do we actually prove this and figure out just how viscous a liquid is? Well, we turn to a total classic, the falling sphere lab. We take a wide, transparent glass or acrylic tube. Usually, it's about a meter or more in length, and it's got to be wide enough so the ball doesn't drag against the walls. Then, we fill it up with a highly viscous liquid, like glycerine. Next, we pop some rubber bands around the tube to mark our specific timing zones. And finally, we take these clean, dry steel balls, we already know their exact radii, and we drop them right down the center of the liquid.
Now here's what's really interesting about how we actually capture the data. By the time the ball reaches the first mark, let's go ahead and call it mark Y, it has already stopped accelerating. It's already hit that perfect state of equilibrium, that terminal velocity we talked about. So all we got to do is start a stopwatch the second it passes mark Y and stop it the second it passes mark Z. And since it's moving at a constant speed at that point, we just divide the distance between the marks by the time it took, and boom, we've successfully calculated the terminal velocity. Of course, we repeat this whole process with balls of different sizes. Then we graph our data. We plot the terminal velocity on the y-axis against the square of the ball's radius on the x-axis. And what do you know? We get this beautiful, perfectly straight line. And the slope of that line is exactly what allows us to calculate the precise coefficient of viscosity for the glycerine. Oh, but wait, actually, I got to share a vital lab secret here from our sources. Before you drop those steel balls, you absolutely have to rinse them thoroughly in the glycerine first. If you just drop a dry ball in, it might trap this tiny little air bubble right on its surface. And let me tell you, that will completely ruin the drag coefficient and totally mess up your data.
All right, let's shift gears a bit. We're moving from deep inside the liquid to its very edge. Have you ever seen a bug just casually walking on water? Or maybe a perfectly spherical dewdrop just resting on a leaf? That brings us to our next big concept, surface tension. Surface tension is this tangential, cohesive force that acts right along the surface of a liquid. You see, because the molecules at the surface don't have any liquid molecules above them, they just cling super tightly to each other and to the molecules right below them. And this intense cohesion makes the surface behave remarkably like a stretched elastic sheet.
But, that elastic skin isn't invincible. There are actually several quirky factors that can completely mess with its strength. First up is temperature. If you heat up water, you're increasing the kinetic energy of the molecules. They start bouncing around way faster, which weakens those cohesive forces, and that drops the surface tension. Impurities are another huge factor. Get this, if you add a highly soluble impurity like just your common table salt, the surface tension actually increases. Crazy, right? But if you add organic substances like soaps, detergents, or alcohol, the surface tension absolutely plummets. Even things like dissolved atmospheric gases, think oxygen or carbon dioxide, they can slightly weaken that surface tension over time too.
Now, to measure just how strong this elastic sheet really is, we use something called the capillary rise method. Basically, when you dip a really narrow glass tube, a capillary tube, into a beaker of water, this incredible phenomenon happens. The adhesion between the water and the glass is so intense that it literally pulls the water up the inside of the tube. It's totally defying gravity, and it only stops rising when the downward weight of that tiny little water column perfectly balances out the upward pull of the surface tension. So by measuring exactly how high the liquid rises, we call that height h, we can mathematically calculate the exact surface tension.
Let's move to the lab and see how this actually works in practice. We have to start by taking extreme care to thoroughly clean our capillary tube. We're talking using caustic soda and nitric acid here, because I kid you not, even a microscopic speck of grease is going to alter the results. Once it's pristine, we clamp the tube perfectly vertical over a beaker of pure water using a plumb line, and we measure that capillary rise. But then comes the magic part. We take just a little bit of detergent, mix it right into the water beaker, and we watch what happens to the height of the water inside the tube.
And here is the crucial takeaway. The second you add that detergent, the water column in the capillary tube literally drops, just physically falls down. Why? Well, it's because surfactants, things like soap and detergent, they have this hydrophilic, water-attracting head, and a hydrophobic, water-repelling tail. So they just force themselves right into the surface layer of the water. This completely disrupts those cohesive forces between the water molecules, instantly dropping the surface tension. And with weaker surface tension pulling it up, the water just can't sustain that high column anymore, so the level falls.
Now, you're probably sitting there thinking, okay, this is neat for an 11th grade physics lab, but why does this matter to me? Well, these formulas are literally saving lives and solving daily problems out in the real world. By understanding viscosity, medical professionals can actually calculate the velocity of blood flowing through your blood vessels. It even lets them figure out the internal temperature of your blood indirectly because, remember, viscosity changes with temperature. And those capillary tests with a detergent, that is exactly how chemists engineer better soaps. They need to efficiently break the surface tension of water so it can penetrate and wash away all that stubborn grease on your dirty dishes.
We honestly take the world around us for granted most of the time. We splash water, we pour oil, we don't even give it a second thought. But think about it. If a single drop of liquid resting in a glass tube can unlock the mechanics of cardiovascular health and chemical engineering, what other everyday phenomena are hiding epic physics battles right in front of our very eyes? It's pretty wild to think about. Keep looking closely at the world around you, stay curious, and I will catch you on the next explainer.